Hey everyone, how's it going? So today we're going to be talking about section 3.1 and 3.2. There's not a big difference between them. So 3.1 is all about talking about quantifiers, and then 3.2 is negating those quantifiers. So I can see why they're two sections, but we're going to kind of talk about them just as they are. We're not going to do section 2.4 or 2.5. So they involve these things called circuits, and they talk about hexadecimals and binary, which are great little fun things, right? Which is why I gave you the lab on binary, right? Because it's kind of a fun thing to learn and stuff like that, but have literally no meaning for the rest of this course whatsoever, right? So if it's not all connected, right, I don't really want to talk about it. So yeah, let's just go ahead and get started. So like I said, 3.1 is about something called quantifiers. So we've made it out of chapter 2, finally, right? And so we're on to chapter 3. And quantifiers is what it means is we're going to learn how to start writing proofs, right? So we're going to be doing the basic of basics, learning how to write statements that we're going to put in our proofs. And we've already been doing this because I've been sprinkling it in kind of throughout the semester here, right? Because I didn't want it just to kind of hit you in the face, right? So I've been kind of sprinkling it in, but now we're going to like formally do it. So let's just go ahead and do it. So the first thing we need to talk about is what the heck is a quantifier. But in order to do that, we have to talk about predicates, okay? So here we go, definition. So a predicate, okay? So a predicate is a sentence, okay, that contains a finite number of variables and becomes a statement when I put in values for my variables, okay, is a sentence with finite variables and becomes a statement when I put in values for my variables. Okay. So, and just like when we talk about functions and stuff like that, how functions have a domain and the domain is the set of things we're allowed to plug in. The same is true, and we still call it domain. So the domain of my predicate variables is the set of values I can plug in. Is the set of values I can plug in. Okay, and we kind of already, know what this is, but we'll go ahead and do it. So here's an example. So if I say P of X is going to be my predicate, okay, and I want P of X to be the predicate X squared is greater than X, okay? And what I want to find P of 2, and let's say P of a half, okay? So all we do, P of 2, it's just kind of like function notation where it says we replace X with 2. So this says that 2 squared is greater than 2, right? This is what P of 2 is. And P of 1/2 says that what? 1/2 squared is greater than a half, right? And now we need to determine whether these are true or false, okay? So the first one, 4 is bigger than 2. Hey, that one's true. But look, this second one here, that's not true, right? Because 1/4 is not bigger than a half. So this one is false. So notice how we we're allowed to plug in something that would give us a false statement. That's totally okay. We just have to say what our domain is. And for us in this one, I just assumed our domain was any real number we wanted. So, since we can get these false statements out, it would be really nice for us to have something where we only took the true statements. And that thing where we only take the true statements is called the truth set. Okay. So the truth set, is the values in the domain, right? In the domain that make P of X true. Okay, so let's go ahead and do an example of this, but I want to write this definition in symbols first. So maybe pause the video, see if you can write this in symbols, and I'm going to go ahead and write it right here. So this is how you write this in symbols. Okay. So this is what the truth set is equal to. It's the set of all X values inside my domain such that when I plug it in, I get P of X to be true. Okay. You can do colons for such that, or you can do the vertical line, whatever you want to do. Doesn't matter to me. Okay. Let's do some examples. Let's find some truth sets. Okay. So I'm going to say my predicate is n is a factor of 8. Okay. I want to find the truth set if my domain is equal to z plus. Okay, so only positive integers. Okay, so here we go. So my domain is 0, 1, 2, 3, 4, whatever, right? All the way up, but doesn't include negative numbers. And I want just the factors of 8, just the integers that are factors of 8. So I get 1, 2, 4, and 8. That's my truth set. So I look at my whole domain and I pull out the ones that make my statement true. So what are the ones that make my statement true? Well, any factor of 8. Okay. Notice it's different if I do D is equal to just the integers. Okay. So I can include negative numbers. Now my answer is -8. -4, -2, -1, 1, 2, 4, and 8. My true set is bigger. Okay. So telling me what your domain is going to strictly affect, okay, what is in your true set. Okay. All right. So that's kind of predicates and stuff like that. Now we want to talk about our quantifiers. So we've already seen them. The main quantifiers, there are 2. There's this, which means for all, which is the universal quantifier. Okay. And then there's this one over here, which means there exists. And it's called the existential quantifier. Okay. These are our 2 quantifiers, and they're going to help us express our thoughts, essentially, is what it's going to be. Okay. So the way that we're going to make it so we only get what we want for our truth sets is to use these quantifiers. So these quantifiers are going to change our predicates into statements. Okay. And then these quantifiers are going to make sure we get the information we want out. Okay. So let's do an example. Okay. So example, I'm going to say H is equal to the set of humans. Okay, so H is a human. Okay. So what I want to say is that every human, so this is the informal way, every human is mortal. Okay. None of us are immortal, at least, not yet, I guess. Maybe science will get there one day and we can live forever. Anyway, so what I want to do is I want to use quantifiers to write this sentence, every human is mortal, in math terms. Okay. And the way I'm going to do it, so this is the formal way, is I have some set H. So I'm going to take it one word at a time. Okay. So every is the same as for all. Okay. So for all humans, I don't know what a human is, so I just make up a variable. A lot of times we use X, but we'll use H for humans. So for all H in my set, so that means for every human being, right? H is mortal. Okay, this is the formal way of writing it, because this says, look at an element in my set, that element is mortal for every element in my set. Okay. Okay. I know it's kind of a weird example, but that's fine. Okay. So we could look at some other examples, right? And try to find maybe some counterexamples. Okay. So find a counterexample. Find a counterexample to, for all X in the real numbers, X squared is greater than or equal to X. So the thing about proving something is when you prove it, it has to be true no matter what. No matter what. So when you try to disprove something, you need exactly one counterexample. So that's why we're going to practice finding these counterexamples. Okay. So I need one counterexample of an X that when I square it, it's less than the original, right? Because a counterexample would be the opposite of this. Okay. So we can choose any number that you want that will work. Specifically, the numbers that will work are some number between 0 and 1. Any number between 0 and 1 will work. So I'll just choose 1/2. So X equals 1/2 is a counterexample. Okay. It's a counterexample because 1/2 squared is definitely less than 1/2. Okay. All right. So those are counterexamples. Like I said, we've kind of been doing this over and over again, right? Now, what if I said this? Is there a counterexample to, for all X in the integers, X squared is greater than or equal to X? Okay. It's the same question. All I did was change my domain a little bit. But the problem is now I'm stuck to integers. Okay, so I need to find an example where if I square it, I'm less than I was before. And you can kind of work through it. So we can check, right? This is not a proof, but you know, we can kind of mentally check, right? That 1 squared is definitely greater than 1, and 2 squared is definitely greater than 2, and 3 squared is definitely greater than 3, and it keeps going, right? 0 squared greater than or equal to, so the equal to counts, right? How about -1 squared? Is that bigger than or equal to -1? Well, yep, now we have positive numbers. A positive is always bigger than a negative. So you can see that no matter for what integer I choose, there is no counterexample. And that's the game we're going to play with the proofs. So sometimes with our domain, it doesn't work. And this is how people solve problems. They look at the big picture and they go, nah, there's a counterexample. I found it. But what if I restrict my domain a little bit more? Is there a counterexample then? And they go, oh no, there's no counterexample if I restrict my domain a little bit. So then they take their restricted domain, they try to just widen it a little more, and then widen it a little more. And they keep widening it until they can't widen it anymore. And that's kind of how mathematical theorems come out, okay? So that's the universal quantifier. We now have this existential quantifier, right? So we could say there is a student in Math 160. Okay, so this is the informal way of saying this. Okay, I just wrote it in a step. Okay, the formal way of saying it, the formal way is saying, so there is a student means there exists a student, not one. There could be 1 or 2 or 3, it doesn't matter. There exists at least one. So there exists a student in, I don't know, people, right? So there exists a student in the set of people such that, which we denote S dot T 99% of the time, such that S is an element of Math 160. Now you do have to define what P is, okay? Where P is equal to the set of people. Okay. So that's what it formally looks like in math language. And, you know, it would be very good to kind of practice writing between this formal way and informal way, because sometimes it's really nice to write formally, right? Be nice and concise. Other times it's not as nice to write formally. So, but that really won't happen for us in this class, okay? So let's talk about our last set of statements here, and it's the universal conditional. The universal conditional, okay? And what it means is if we have for all x, if P of x, then Q of x. That's what it means, okay? That's the universal conditional statement. So no matter what x I pick, if P of x is true, Q of x is true, okay? No matter what x I pick, okay? So let's do an example of this, okay? So an example is for all x, element of the real numbers. Okay, so there we go. That's my first part. If x is greater than 2, x squared is greater than 4. Okay, then x squared is greater than 4. This right here is a universal conditional statement. Okay, this is formal. This is very formal. What if I tried informal? What would that look like if I wanted to do informal? So if I wanted to write this informally, there's a couple different ways I could do it, right? And one of the ways is this, is if a real number is greater than 2, is greater than 2, its square is greater than 4. Okay, that's the way of writing it, where it doesn't have all the symbols and stuff like that. You could also say the square of any real number greater than 2 is greater than 4. You could also say whenever a real number is greater than 2, its square is greater than 4. It really doesn't super matter as long as you make sure you get all the pieces of information. And what are those? You have to be a real number, okay? You have to be bigger than 2, and then your square is bigger than 4, okay? So there's lots of examples and stuff in the slides if you want to work through them, right? But I'm going to talk about prime numbers right now, okay? And we're just going to introduce them because we're going to be doing a little work with prime numbers a little later. So we're going to introduce some prime numbers. Hopefully everyone knows what a prime number is, okay? But if not, let's talk about it. Okay, so a prime number is an integer, right? Got to be an integer, greater than 1 whose only positive integer factors are itself and 1. Whose only positive integer factors are greater than 1. Okay. So let's look at this statement. Okay. There is an integer that is even, okay, that is even and prime. What I want to do is I want to write this formally, okay? So there exists an n, don't know what it is, such that this is the notation we use. Prime n means it is a prime number. That's our and. Even n, that means even number, okay? In fact, right, there's only one of them. And the only one of those is 2. There will be no other even prime numbers out there because if, let's just think about it, this is going to be a proof by contradiction, okay? So you assume there's another even prime number, okay? We'll talk through it, okay? But I won't write it down. Assume there's another even prime number, okay? Well, since that number is prime, the factors are 1 and itself. However, you can show that every even number is divisible by 2, which means the factors of our even prime number would be 1, 2, and itself, making it not prime, which is against our assumption. Therefore, there can't be another even prime number. Okay, so how I just walked you through that is proof by contradiction. Okay, and we'll talk about this more formally later. But we essentially just proved, or I just talked, but I said it very how I would write it, right? Just showed that there can only be one even prime number. Okay. Some other facts about prime numbers that I just kind of want to show you and talk about is there's something called the twin primes. Okay. So let's talk about these twin primes just briefly. Okay. This is more for you. And if you want to look up the twin primes, go to YouTube and look up something called Numberphile. Maybe you know this, maybe you don't, and look up the twin prime conjecture. Okay. What is a twin prime? Okay. Well, a twin prime is a prime number, okay, that has a prime number exactly one odd number away from it. Okay, so let's do some examples of twin primes. 3 and 5 are twin primes because they're one odd number away from each other and they're both prime. Okay, 5 and 7 are also twin primes. Those work. Okay, 11 and 13 are also prime or twin primes. Okay, 17 and 19 also work. Okay, and then I don't know what the next twin primes are. It's not 23 and 25, no. Maybe 29 and 31. I don't know. Are those prime? Maybe. So 29 and 31. I think those are the next twin primes. Okay. The conjecture, so this is what the twin prime conjecture asks. Okay, what it asks. And no one knows, that's the reason it's a conjecture. Okay, the twin prime conjecture says, will this always happen? So will there always be twin primes no matter how high I count? Okay. That's what the twin prime conjecture is. So if you want to look it up, go ahead. I thought I'd mention it. And yeah, so that's what we're going to talk about with primes. We're going to talk about prime factorization. Primes give us a lot of really cool things in something called number theory, right? And so you'll notice Numberphile, there's number theory. It's like a branch of mathematics. And it's all about this kind of stuff, like how far apart are the primes? You know, is there always twin primes? What happens when I do modulo arithmetic, which we'll do later, with prime numbers? Is there a way that numbers are always going to work out, right? And so I want to give you this just so you have some tidbits of information that aren't necessarily in the book or in the slides. Okay, so that's 3.1. Okay, so now we're going to talk about 3.2, which is really just negations of our quantified statements. Okay, so I'm going to start with a definition. Okay, and then we're going to do some examples, and that will really be it for 3.2. Okay, so the negation, okay, of for all x in D, Q of x. Okay, so the negation of this is, so you basically start with each group and you need to negate everything. So the negation of for all is there exists. Okay, so there now exists in X and D such that now I need to negate Q of X, not Q of X. Okay. So this is going to be important because sometimes we need to negate our for all statements. And so the negation of our for all statements is going to be exist statements. And surprise, surprise, the negation of exist statements. Okay. So the negation of existential statements Okay. So if I have there exist an X element of D, Q of X, right? This is my statement. So the negation of this is, well, you do the same thing. The opposite of there exist is for all. And then the opposite of Q of X is not Q of X. Okay. So let's practice. Okay. So let's say negate. Okay. Negate for all P element of the prime numbers. Okay. P is odd. Okay, I want to negate this. Okay. So the way we would negate it is we start with our first part. Okay. So the opposite of for all is there exists. So there exists a P in the prime. And then I need to negate P is odd. So you could say P is not odd, that's fine, but not odd means even. Okay, so P is even. Okay, that's our answer. Okay, so we're gonna have to practice negating statements like these. So we could do some more, right? Let's say, okay, for all politicians, X is not honest. Okay, so let's negate this. Okay. So the opposite of for all is there exists. So there exists a politician. X such that X is honest. Okay, so this is formal. This is very formal. Let's just do a double check. If I were to write this informally, what would this say? So there exists some politician that is honest, or you could say some politicians are honest. Okay, these are one and the same statement. Okay, so being able to negate and then switch to informal, right? It may seem kind of weird at first, but that's okay, right? It's just lots of practice, okay? So we talked about universal conditional statements as well, right? And so we want to negate the universal conditional. Okay, so if we want to negate the universal conditional, well, then what are we really trying to negate? We're trying to negate for all X if P of X then Q of X. Okay, so this is what we're trying to negate here. So what this means, so this is logically equivalent to, so I kind of move my way along, okay? So first, the for all statement. So there exists an X, okay? There exists an X such that P of X and not Q of X. How did I get this? How did I get this statement? Okay, let's remember here that if then statements can be written as or statements. Okay, so the negation of P of X then Q of X, okay, is really the negation of not P of X or Q of X. So if I were to negate this, I get P of X. Okay, so logically equivalent to P of X and not Q of X. Okay. So this is going to help us out a lot. Okay, so being able to switch from if, then, and ors to ands and like just trying to keep it all straight. I know it's a lot, right? But make yourself a chart. It really does help. Okay. So where do these come from? Right? Well, they're basically just De Morgan's laws, right? What it says is the negation of an and statement is an or statement, right? And the negation of an or statement is an and statement, right? Well, you can think about it the same way. Universal statements are just big generalizations of and statements. And existential statements are just big generalizations of or statements. So when you negate the universal statement, you just get the existential statement. Okay. And it's that way on purpose. Okay. So that's really all I want to talk about from section section 3.2. Okay. There's stuff about the contrapositive, converse, and inverse in the slides, but we've already talked about the contrapositive, converse, and inverse, right? And the way we did it was exactly how they do it in section 3.2. Okay. So you can also, you know, for the contrapositive, it's you negate it and then flip it, right? So it's the same thing, right? You're going to have to know how to negate. It all comes down to knowing how to negate. Okay. So let's just, let's just go from there. And next time we'll do section 3.3.